you go to, well, in this case, as I have already an account, it is going directly to my account. But let me log out here for you to see what you get. Sign out. So now this is what you get when you enter this page, wolframcloud.com. This is where you get here. And then if you already have an account, you can sign in, or it is going to send you directly to your account like my computer does. But if you don't have this is the first time, you have to sign up. You can sign up for free. So you click here, and this is the information that they are asking you to enter to sign up for free. So you need to enter an email. You need to enter your first name, last name, and the password. You have to confirm the password and to click here, agree to terms and services, and then you create your Wolfram ID. And that's it. Once you create your Wolfram ID, next time that you go there, what do you have to do? You can enter again wolframcloud.com, and then you sign in and you get access. But when you sign in, this is what you get. I already have this open. Well, let me show you well, here they're asking me to sign in again, so I'm going to enter my email, which is my college email, and then I'm going to enter my password, and I entered it. I already have opened something here, which is what we're going to discuss with you. But in general, when you don't have anything open, it goes here. You click on this this symbol that looks like a star. This is what you see the first time that you enter. New notebook allows you to enter to create a new notebook, or My Files gives you access to all other notebooks that you have opened before. And then in this case, if you want to create a new notebook, you click here. You need to have a notebook to do calculations. So let me show you an example. Let's say if I want to create any new notebook, you click here and you can name the notebook. You see, so far this notebook is unnamed. Now, if you click on the little pencil that looks here, that appears there, then you enter the name of this. This is a test notebook. Just to illustrate the point. And then you need to click on the check mark here. And that's it. You have created a new notebook. Now, look at this. Every time that you are going to enter by default, whatever you enter the first time when you start is going to be like a piece of code. For example, you can enter 2 + 2. And then because you can use Wolfram Mathematica or Wolfram Language to do calculations, 2 + 2, and then if you want to evaluate that, you need to press Shift plus Enter, Shift and Enter, Shift and Enter, and you get the result. You see an input and then the output. Now, in the right side here, you see that there are a big bracket here, and inside this big bracket, you have 2 small brackets. The first small bracket encloses the input. The second one encloses the output, and the bigger bracket that appears outside encloses both the input and the corresponding output. And now, but this is not the only kind of things that we can enter when you are creating a notebook. You can enter also other things, like, for example, you can, you click here, you can go to, well, you have a free-form input. A free-form input is an input where you ask, you query is written in form, and not in a formal language, but in an informal language. Let's say, for example, add 2 and 2. Let's see what happened when you enter that. Now you press Shift Enter, and then you get the same result as before. You get adding to you enter your query in a regular language, and then you got the result, the same result that we got before. Now there is another way of entering something into Notebook, which is like a Wolfram Alpha query. You click here, this is the symbol that tells you that this is what you are entering now. And you can do something similar as before. You can enter anything like you do, I mean, using regular language. You don't have to use a very specific language. You can describe what you want to obtain. And then you press Shift and Enter, and you get the output as it is given by when you use Wolfram Alpha. You know, Wolfram Alpha is this website, wolframalpha.com. It's a website that allows, well, where you don't have to open an account to use Wolfram Alpha. You can just go to wolframalpha.com, and then you enter anything, you know, add 2 plus 2 or 2 and 2, and then you press Shift. I mean, you have to press Enter now, and then it give you a whole answer here. Well, it give you the result, but it explains a little bit more. I mean, it give you some interpretations or some facts which are related to that result. For example, here they tell you that this is a graphical interpretation, okay? And then, so these are some typical human computation times and so forth. And then this is gonna be what we are seeing here. Let me go back to this. Yeah, this is what we are seeing here. And one of the features of Wolfram Alpha is that you can see the step-by-step solution, And when you go to Wolfram Alpha directly, the step-by-step solution is available only when you are paying for the professional version. But in this case, you can always see the steps, no matter whether you are paying or not. So this is a real advantage with respect to just using Wolfram Language. If you click here, you get what? Well, they tell you some explanations, some possible steps here. And then this is something that applies not only for simple additions, it applies for limits, for derivatives, or for integrals, for solving equations, and so forth. Now, let's go to the notebook that I prepared for you. I have this notebook over here. So here, I need to go to my files. Well, it is already here because it's the most recent file that I opened there. And then I have to let the system to load properly. You see there is a blue line here that is moving to the right, indicating well, the point at which we are with respect to the leading, I mean the system loading this notebook. And then we are almost next to the end. Okay, now what we are seeing here is my notebook. Let me tell you something. When you press, let me go back to my previous notebook. So when you, and we were talking about the types of inputs. I told you that if you press Wolfram input, which is by default what is always going to appear here, you can enter something, but it has to, well, it has to meet the Wolfram language input requirement. It means it has to be written in a certain way for the program to understand that. And then the next two, you can enter just your input using regular language. For the next one, you can enter plain text. It means when you don't want to enter a code, but you want to enter a comment or something, you can use this, or you can also use Alt +7. And then when you click on other styles of text, you get the styles that can be title, subtitle, section, subsection, subsection. We also have text, of course, and we have the input as you enter it in code, you know, code or input or out. Now, when you are getting, I mean, if you want to prepare a new notebook and you want to start with the title, you go here to other styles of text and you press title. And now the style of this cell that is indicated by this bracket is going to be title. And then this is testing the title, for example. And this is going to be the title of your notebook. And now you can enter everything afterwards. It's going to be, can be text, or can be introduction, or can be a subtitle, or if you want to enter a section after that, you have to click here. Notice that you press enter and you get the cursor here. Sorry, we need to go back to press backspace, and then if you put you click here next to the, I mean, just after the cell of title, you see a horizontal line with a plus in a circle here. This is where you have to click to get the different forms of inputs that you want to for this cell. Or the different kinds of formats. If you want to enter, let's say now section, you go to section. You click on section, and then you can say, well, this is a first section. Notice that the type of the color, the type of, well, the size of the letters is a little different from title. Okay. Now after that, you can enter just text. Let's say plain text. You have this option here. You click here, and you can say this is a test for for trying, you know, a text. Okay, well, now after that, you can show examples where you use code. For example, you can use, let's say, you can make x equals 1, and you can make y equals 2. And then you can go down below that, and you can enter x plus y. So basically, x plus y. And then if you press enter, then the system is going to do all the operations represented here. It means it's going to make x equals 1, y equals 2, x equal 1, y equal 2, and then it's going to find the x plus y. Let's press shift enter, and you get that the x is 1, the y is 2, and the x plus y is 3. And then this is the way in which we start a notebook. So now, well, the first paragraph is about different types of cells. You're going to see what I have explained to you. You can see this here, different types of cell. Remember, for example, this cell here is just text. Well, let me go back to the beginning. This cell, the first cell represented by this bracket, is title. The next one is subtitle. The next one is a section. This is an introduction, is section. This another the different types of cells is also section. And this part here is text. You see that I have text here. I introduce text here explaining the introduction. And then, well, this is the same thing here. They explain the different kinds of inputs. And then there are some examples. For example, the example, graph the function y equals x to the second using Wolfram Language input on the closed interval from -3 to 3. In that case, you need to know the built-in function plot, and then you need to enter that function here, and notice that it follows certain rules. Is plot, and then everything that is inside, well, you need to put brackets after plot, and then inside the brackets, you have to put the function first that you want to plot, and then the interval. And the interval is for the values of x. So the x goes from -3 to 3. And then now, you can put the cursor at any point on that line, and then you press Shift-Enter to evaluate that expression. And when you do it, you see that the program is doing the evaluation. You see, and then it returns the output corresponding to this input. Now, the same example, but using a free-form language, so a free-form input. You put the cursor at any point here, you press Enter, and in this case, you get this shouldn't be okay. This shouldn't be okay. There's something happening here. Let me change my function for a moment. Let me put 3 here instead of 2. Well, remember that let me see. Let me start clearing the value of the x. Something that can happen sometimes. Clear the value of the x. And then you press Enter. And now let's do it again. So Shift-Enter. And now you see that you get the graph. But I want to get the graph of y equals x to the second. Let me return. Let me go back and put the value 2 for the exponent. So you press Shift-Enter and you get what? You get the parabola pointing down, but this shouldn't be okay. There is something weird here. Let me enter clear the y also before doing this. And then let me press Shift-Enter, put the cursor there. And now I got, yes, it is, sometimes I have to start clearing the variables that I have to use, because otherwise I might get something that is not what I want to get. And then, well, in the last situation here, in the last example, we are going to do the same thing. We are going to graph the function y equals x to the second using Wolfram alpha input on the closed interval. Remember, to make this input Wolfram alpha input, you will need to, remember, you need to do this. If you put the cursor after any cell and you press Enter, you're going to get a horizontal line. Then you're going to click here on this little circle with a plus, and then you're going to enter you're going to press to click on Wolfram alpha query, and you get that symbol. And then you can write down your question, your query using a regular language. So let me erase it. Let me erase it from here. Let me erase the cell corresponding to that. This is what I have here. Oh, I erase everything. Okay, this gives me the possibility of entering the whole thing again. So I'm gonna do it. So here you click on the plus, then you go to Wolfram alpha query, and then My query is graph the function y equals x to the second on the interval from -3, sorry, from -3 to 3. And then you put the cursor at any point on that line and you press Shift and enter. And then what do you get? Let me close this message. This is taking too long here. And then what we obtain here is an output which is very similar to what you would obtain using Wolfram Alpha, which is this page here that I mentioned before, wolframalpha.com. When you enter something, you get an output. So this is similar. And even you can see, well, for some of the, well, you see that it returns the graph, but it also identifies the curve, which is a parabola. It gives you also some related results, like, for example, that it finds the arc length of that curve, the arc length of which is given by this formula. And then you can see here the step-by-step solution for this part. So remember, this in general doesn't work unless you use Wolfram Alpha and you have a professional account. That means that you have to pay something, or you have the application. The application is cheaper. But now, what I said here, notice that the difference between the last output and the other outputs. The last output is similar to the one that you would obtain when you use Wolfram Alpha. Now, let's move to expressions. So basically, what we're going to start seeing here, we're going to start seeing many basic things which are essential for you to understand how can we apply Wolfram language to differential equations, to solve some differential equations. We're, of course, the most basic differential equations. But, well, in Wolfram language, everything is expression. Even numbers are expressions, are represented by internally by the system like expressions. For example, an expression is what? Imagine like a function of one variable, f of x, that has a name, which is the letter f, and has some arguments. In this case, only the x. Or for example, f of x comma y is an expression that contains two arguments. Or f of x comma y comma z, and so forth. It can have any number of arguments. And then the f is what we call the head of the expression. The x, y, and z are called the arguments of that expression. One example of a expression is the absolute value of a number. We can enter absolute value, to enter the absolute value of x, we can do it like this. Absolute value of x. Let me clear the values of x so that from the beginning, so that if any value is given before, it doesn't come out here. So when I enter clear x, this is another example of expression. Clear, the head is clear, and the only argument here is the x. But in this case, how does it work? It clears any value of the x. And then we have this. Now, if you enter dx by itself and you press Shift Enter, it returns dx. This tells you that dx doesn't have any value. Now, let's go to this other expression, abs of x, which is absolute value of x. If you press Enter, you get absolute value of x, because in this case, x doesn't have any value. But if you enter absolute value of a number, let's say of -3, you get 3. This is another example, plus x comma y. This is the function, the built-in function that takes the values of x and y and add them and obtains the sum of these two values. You press enter. In this case, you get x plus y. Notice that the y doesn't have any value. If it has a value, it's going to appear here. But then if you don't want any value for this, you need to clear that value before doing that. You can do it like this. Clear the y. I already cleared the value of the x before, and I haven't assigned any new value for that. And then when you press plus xy, you get the sum. It indicates that this is going to be the sum, and it uses for the output, it uses here the regular way of expressing the sum of two expressions or numbers. Then, for example, when you apply this function to two concrete numbers, you get what? You get the sum of the two numbers. Now, in this case, when you enter x plus y and you press enter, you get x plus y again. Remember, x and y, they don't have any value, but what I want you to notice is that plus x comma y is the same as x plus y. So this is like a shortcut, an abbreviation for that expression that doesn't show the head of the expression or the arguments. What is the head? What are the arguments? But it's equivalent to plus of x comma y. Now, if you enter 2 plus 3 here, the program is going to add the two numbers. Notice that absolute value of x is an expression with only one argument. Plus of x comma y represents the sum of the number x and the number y. That can be also entered in this way, x plus y. We can have an expression with more than one argument. For example, if you enter times x y, x comma y comma c, this is going to multiply the x times y times c. Notice that when the x, y, and c, they are not representing any values, then you get the same variables again, x, y, c, separated by spaces. Well, there is a space here in between x and y, in between y and c, there is another space. And then you can also find the same thing by entering x times y or asterisk y, asterisk c. You press enter, and then you get the same thing, the product, the multiplication of those expressions. There is another way of finding that, which is just entering x space y space z. And then you press enter, and you get the x times the y times the z. Let me show you an example. Let's say, in this case, I'm making, notice that when I write down, everything that I write down here in a separate line, is going to be like a separate input. In that way, I can enter many inputs together in one input. So all these inputs together, I make the x equals 1, I make the y equals 2, I make the z equals 3, and I find x times y times z. When you put the cursor, notice that there is only one cell for the whole thing, which is this cell here for the whole thing. If you put the cursor at any position, then, and you press shift enter, you get the inputs one by one. The input for the first entry, the outputs one by one. So the first output is the one corresponding to the first input here. X is 1. It returns that it is 1. Y, you made it 2, and then it returns 2. The Z, you made it 3, so it returns 3. And now the other input is to find x times y times z, which is 6. Okay, I can also find now the product in a different way, like a space y space z, and I press enter, and I get what? I get 6. But if I enter x, y, z, x, y, z, without leaving the spaces in between, then when you press enter, it doesn't identify this as a product. It considers this as a variable. Okay, as a variable. And this is what I explained here. Well, no, in the last examples, we gave values to x, y, z, and we found the product. Notice that we enter x equals 1, y equals 2, z equals 3, and then x times y times z in different lines, okay? And this is telling the program to show all separate outputs. One for the outputs are going to be 1, 2, 3, and 6. It means if you want to continue using those variables in what follows of this notebook, you have to clear the values as soon as you realize. So then you press enter here, and it doesn't return anything because in this case it doesn't have to return anything. We have cleared the value. But if you want to check that the program has cleared all the values, you enter the x, the y, and z as separate inputs, forming part of the same cell, and then you press Shift Enter, and you see that it returns the x, the y, and the z. This is it is telling you that the x, the y, and z has been cleared. And this is what I was explaining to you before. To represent the product of x, y, and z, we shouldn't use x, y, z without leaving spaces in between the x and the y and the z, because the system understands any combination of letters or combination of letters and numbers, as long as you don't start with the number as a single variable. A variable, this is going to be the name of that variable. Okay, so example of variables are a, b, c, or yz1, or my variable. So these are combinations of letters and numbers, but they can never start with a number, because when they start with a number, they consider that this is a multiplication of that number by what follows after the number. And then this is an example here. If you enter x equals 1, y equals 2, yz equals 3. Now I'm using semicolons. Well, the semicolon tells the program that these are going to be inputs. X equals 1 is the first input, y equals 2 is the second input, z equals 3 is the third input, and the x, y, z is the last input, but it's going to show you only the result for the last one, for the last input. But when you press enter, notice what happened, you get x, y, z. It means that even though we know that the x is 1, y is 2, and z is 3, the x, y, z doesn't return any value, it returns the same thing. Why? Because this is just a symbol that is representing a new variable, different from x, different from y, different from z. If you want to find the multiplication of these three variables for which we have given those values, you have to enter x times y times z, and you press enter, you get 6, or you can enter them leaving this separation between the x and the y and the z. One space in between, and then you press enter, you get the product. Now notice that you can use times to represent the multiplication. Well, in this case, this is a variable. If you try, you can use the function head. It's a built-in function that allows us to find the head of that expression when the expression is not written in the formal way, in the regular way, or the standard way. Then you put the cursor here, you press enter, and it says, well, it gives you the three outputs here. For the first one, it tells you that the head is symbol. So it means that the kind of expression here is a symbol, is a variable. For the second one, it tells you that, well, it calculates first the x, it does the calculation first. This is x times y times z is 6, and the head of 6 is integer. Okay, and for x times y times z, integer, because it's an integer. But if you do it like this, let's assume that you clear again the values of x, y, and z. I'm going to clear x. I want to clear at the same time the y. I want to clear the value of the z. So I put it like that. I press Shift Enter, and I obtain, well, this has been clear already. You can check it if you want. But if you enter again head of x times y times z, you see that now it returns times, because now it's not finding the result first as we did before when we replaced the x, the y, and the z by 1, 2, and 3. It returns times. Why? Because remember that you can write down the multiplication of 3 variables x, y, and z can be expressed also in the way times, and then the x, comma, the y, comma, z. In this case, if you put the double equal sign here, this is just a logical statement that can be true or can be false. In this case, it has to return true. Why? Because the expression x times y, this is a shorthand. What we have in the left side is a shortcut for the expression that appears in the right side. So when you press enter, it returns true. Now, parts of an expression. You can represent expressions by using other variables. Like in this case, we have an expression f of x, and you can represent that expression by f of x. So when you put the equal sign here only once, it means you are assigning whatever you have in the right side to the left side. And then, well, here, if you press enter, you get that the expression that you have, we have denoted that expression by this notation, EXPR. Now, you can find parts of that expression by using a double bracket and then a number and double bracket. So here, when you enter the expression double bracket 1, it is going to return what? Only the x. Only the x. When you enter the whole expression and then double bracket 1, it returns the x again. It's the same thing. So this is very convenient because sometimes we have an expression and we want to get rid of the head. We want to get only one of the arguments, or all the arguments, or the list of all the arguments, and then this is what we can do to do it, to get it, okay? For example, imagine that you have this expression here. The expression is absolute value of x to the second minus 2 times x. And we want to eliminate the absolute value in front of that expression and to get access only to the expression, the algebraic expression, which is in between the brackets. How can you do it? Well, you can first, let me define expression, well, exp1, a new variable is gonna denote this, the absolute value of that. So you press, you put the shift, I mean the cursor at any point of this line, and then you press shift enter, and you get that this is the expression that we are denoting by that. Now, if you want to get the expression which is inside, you can do it by using exp1 double bracket 1 double bracket double bracket. And then this is going to return what? Just the expression. It means it's going to eliminate the head and it's going to take the expression inside. Okay, now imagine that in some cases we have an algebraic expression like this one here. Okay, well, that expression contains a multiplication and then an addition. Well, first the addition of x and 2. The subtraction of x and 3, and then the multiplication of x plus 2 and x minus 3, and then the addition. It contains many different operations. This is like the regular way of writing this down in real life, but in the program, this is the shortest way of writing this down. Later, I'm going to show you that how can the program internally, the program understands this in a certain way using the different expressions. It's like a composition of different expressions. But then here, I'm going to define exp2 like that expression. Let me press enter to enter that definition or this assignment. Now, what is the full form of expression number 2? me show you. You press Shift Enter here, you get that. You see here, you see the full form. This is internally the program, the system understands that expression in this way. You see, first it adds -3 and x. It adds 2 and x. And then these two results are multiplied because you have the times here. And the times is added to 7 because we have the plus outside. And then how can we get the different parts of that expression? If for the expression 2, if you enter, you put expression 2 or exp2 double bracket 1, this is going to return what? This is going to return, well, sorry. I'm doing the 4 inputs at the same time. And then here, you see that when I enter exp2 double bracket 1, it returns only the first argument of the plus, which is the last operation applied, the last expression here, the outest expression. So it's going to be 7. If I put the 2 here instead of 1, it is going to return the other argument, which is times of plus -3, x plus 2, x, which is this product. And this is the second one. If you want to obtain other parts of the second product, for example, the first factor or the second factor, you can use exp2 double bracket 2, 1. This returns what? The first factor. And the exp2 of 2, 2 returns the second factor. But if you want to return the -3, notice that you want to go one level deeper. The depth would be even, you need to go even deeper into the expression. And that's why in this case, the first 2 here represents that you are going to go for the first, for the outest expression here, for the plus expression, you need to go not to the first argument, but to the second argument. This is the meaning of the 2. The meaning of the other one means that it's going to be what? It's going to be that you need to go now to the first of the 2 arguments of times, which is plus or -3, x. And then the next one here tells you that out of the 2 arguments of plus, you need to pick the first one. So it means that's why this is going to return the -3. Let's check it. You put the cursor here at any point of that line, you see that the cursor, let me move it inside. For example, it can be at any point. You press Shift Enter and it returns -3. It returns -3. Now for the second one, it is going to return what? It is going to return, it goes for the outest expression, which is plus, whose heads is plus. It goes to the second argument. Then for the expression here, which is times, it goes to the second argument. And for that expression, it goes to the first argument. So it's going to return the 2. So it means that here, you put the cursor at any point on this line of the input, and you press Shift and Enter, and you get 2. Okay. Well, this is an explanation of what I told you before. The first 2 represents that you go to the second, to this, the second argument of the outest function, which is a plus. Then it's going to be times of this. Then the next 2 indicates that you go to the second argument of this previous function, which is plus 2, x, and the one tells you that it goes to the first argument of this expression. Now, this is a good exercise to practice. This can be, for example, the following. Imagine that I ask you, well, find, given a polynomial, this is a polynomial, notice that you have 4 times x to the third plus 4 times, we can leave the space here to make it more easier to understand, and then the space here, And then for that polynomial, we need to find the product of the coefficients. And then we are going to enter the polynomial. We're going to enter this polynomial. We are going to call it the exp3, which is the name of this variable. So we put the cursor here, you press enter, and then you get the polynomial. Now we can obtain the full form of this just to see how it looks like. The full form, notice that the last operation, the dominant operation here is the addition. You are adding -2 and then 5x, then 4 times x to the second, 4 times x to the third. But if I ask you, well, if you enter exp3 double bracket 1 double bracket, it is going to return the -2. It is going to return the -2, which is one of the coefficients. In this case, it's going to be, what coefficient is going to be the constant term. But if you enter the exp3 2,1, then it's going to go, the first two indicates that goes to the second part here, which is times of 5x, and then the one tells you that I'm between 5 and x, it picks 5. That's why the result here is 5. Then the exp3 double bracket 3,1 double bracket, the 3 here indicates that you have to go to the third argument of plus of this expression, and then in that argument is going to pick the first of the two arguments. Notice that 4 is the first argument of that of these times here, and power of x comma 2 is the second argument. So it's going to pick the first one, which is the coefficient, and for the last one it is going to do the same thing. It means exp3 double bracket 4,1, and then it is going to pick the first the coefficient. And then notice that you have obtained -2, 5, 4, and 4, which are the coefficients of the original polynomial, -2, 5, 4, and 4. And now you want to find the multiplication, the product of these coefficients. The only thing that you have to do is to multiply all these expressions. The exp3 double bracket 1 times the other one here with double bracket 2,1, and the other one here in between double brackets, the 3 and the 1, and so forth. And when you do that, you get the multiplication of these numbers, which is -160, isn't it? So it's going to be -160. Now we're going to introduce lists. Well, what is a list? A list is any finite collection of objects, which is very important. It's a way of representing collections of different objects in this program. And then the objects can be of whatever nature, mathematical nature, of course. They can be numbers, they can be matrices, they can be vectors, they can be lists. So we can have lists of lists. They can be functions. They can be just variables, etc. Then, for example, this is an example of a list whose elements are variables. Notice that a list is another kind of expression. In Wolfram language, everything is an expression. All the objects that the Wolfram language have to deal with are expressions. So here, if you press, well, let me tell you something important here. I'm using the symbol for percent here, the percent symbol. The percent symbol can be used when you want to represent the last output. The percent symbol here represents the last output. So it represents the list formed by x, y, z, which is the last output. And then you press enter, shift enter, and you get the full form of the list. The full form of the list is always like this. The head is always list, and then the elements of the list are the arguments of that list. So it means we can see any list like an expression. that has a head. The head is always list. And that head, I mean, this doesn't indicate that you do anything with the x, the y, and the z. Like, for example, when the head is times, you know that you multiply x times y times z. In this case, list here indicates that you don't do anything with the x, the y, and z, but you consider them and in a certain order, and you don't change the order at any moment, you know, the x, the y, and the z. And then what is the head of the list? As I told you, is list. You see, if you put the cursor at any point here on this line, and you press enter, you get list. Now, let me show you some examples of lists. For example, we can name we can use variables to denote a list. Like in this case, list 1 is the list formed by 1, 2, 3. We are assigning that list to that variable, which is called list 1. So, and we are assigning this other list formed by 2, 2, and 5 to another variable, which is list 2. And then notice that they form part of the same input, but on different lines. So the program is going to give you the two outputs here. So you put the cursor, let's say, at that position, you press enter, and it returns the two outputs, the first list and the second list. Now, you can add lists, as you do with numbers, in the way that you do with vectors also. Well, if you put the cursor on that line and you press enter, you get the sum of the two lists. Notice that what the sum represents here is the sum of the arguments one by one here. 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 5 is 8. Now, you can multiply a list by a number. When you multiply the list 1, which is formed by 1, 2, 3, by the number 3, you get what? You get 3, 6, and 9. So it means you multiply a list by a number like you do when you are multiplying a vector by a number. You can add a number to a list, and what is going to be the result? That number 2 is going to be added to all the components of that list, all the arguments or the elements of the list. And then let's put the cursor here, let's press Shift Enter, and you see that the original list was list 1, that it was formed by the numbers 1, 2, and 3. Now, when you add 2, you are adding 2 to each one of these entries. 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, which are the numbers that we have obtained here. Now, if you apply, this doesn't happen with all the functions, but some functions like the square root of 2 can be applied to a list. And then it is going to take the square root of every element of the list. So you put the cursor here, you press enter, and you get what? You get 1, a square root of 2, and square root of 3. Let me tell you something important. When you enter a square root of a number like 2, in Wolfram language, you always get the number like this, the symbolic form of that number. You want to get a numerical value, you need to use the function n. The function n is going to give you the numerical value. So you enter n square root of 2. You close the bracket, and then this is going to return what? Well, I made a mistake here. You see, I'm getting an error message. Why? Because I enter one additional bracket here that doesn't go here. And then you press again Shift Enter, and you get an approximate value for that. If you want to get a better approximation, you put a comma, and you can enter the number of digits. You want to get an approximation with 20 digits, you press Shift Enter, and you get now the square root approximate rounded to 20 decimal places. It can be up or it can be down. Now, when you take, going back to the list, when you take a list and you, so here, let me erase these two entries. I can leave them here. Okay, well, now, when you go to the list number 1 and you raise it to the second, it means that you have to raise every element of the list to the second. Remember, list 1 contains the elements 1, 2, and 3. When you put the cursor here and you press enter, you get the numbers 1 to the second is 1, 2 to the second is 4, 3 to the second is 9. Now, as I told you, there can be lists of lists. So lists whose elements are lists, like for example, this list here, I can assign a name to that list using a variable that can be, for example, this word here, list 3, and then list 3 is going to be equal to that list. So here, if I put the cursor here and you press enter, you get the same list. If you do it here and you press enter again, you get the same list. You get that. This is going to be the output. Now, for that list, I can get any parts as I did with the expressions. For example, you want to get the first argument of the list, the second argument, the first argument of this list, or the first element of the list is 1. The second element is the list formed by 2 and 3. The third element is the list formed by one list, which is 4,5, and another element, which is 7. And then you want to get all the 3 elements of this list. The first one is a number, the second one is a list, the second one is a list that contains a list and a number. Then you enter this in this way, the list 3, and then the 1 between brackets for the first element, list 3, then the number 2 in between brackets for the second element, and list 3 for the third one. Well, we can enter all these inputs together. So you put the cursor at any point in the input, you press Shift Enter, and you get this, that the first element of that big list here, or relatively big, of the bigger list, I mean, in comparison with the elements is big. And then, well, the first element is 1, the second element is 2, is the list formed by 2, 3, the third element is the list whose first element is a list formed by 4 and 5, and the second element is 7. Now, you want to get access, let's say, to the number 3, the number 2 here. What do you have to do? You have to enter 2 indexes. 2 to express that you want the second term of the original list, and 1 to get the first of the 2 elements of the list, which in this case is 2. But if you want to get the 3, you need to enter 2, 2. Okay, let's see that this works here. You see 2 and 3 respectively. Now, if you want to get elements here, let's say if you enter list 3, double bracket 3, 1, it is going to go to the last element of that list. And then the 1 means that the first element of that list, which is a list formed by 4 and 5. And when you put 3, 2 here, it means that it's going to return the 7, which is the second element. Let's do it to check that this is going to be the result. You see, the first element is 4, 5, the second element is 7. Now, if you want to go to the 4 or the 5, you need to use one more index here because of the depth of 4 and 5. So it means you put list 3, 1. 3, 1 is what returns this list, and you put 1 for the first element, 2 for the second element. So when you press Shift Enter here, you get the 4 and the 5. Well, in Wolfram Alpha, the variables are used pretty much like you do it in mathematics. They can start for a value, or can be used just like symbols as we do in algebra to express, for example, identities. So it means that not every variable has to represent a number. Some variables can stand by themselves and can be used just to see that something like this is true, like a symbolic expression like x plus 1 to the second is the same as x to the second plus 2x plus 1. then the name of a variable can consist, I told you this before, can consist of almost any combination of letters and numbers. And there is an exception here. What is the exception? That we can never start with a number. For example, XOY3 can be the name of a variable, but 3XOY means 3 times X or Y. And then let me show you an example here. Let's say X, if you make X or Y equal to 3, 3X or Y is what? Well, let's do it. Let's run these 2 inputs. When you press enter here, you get 3. When you press enter here, you get 3 times 3, which is 9. If you have something like this is just the name of a variable. Remember, you can for you to see that this is not a multiplication, you can also use what? You can use also let's put a semicolon here, and then we can ask for the head of that expression. If this were a multiplication, then the head would be times. But in this case, let's see what it returns. So here, you see, it returns symbol. It means that this is not a multiplication. And then, but if you make that expression equal to 4, this variable equal to 4, you are going to see that it returns 4. And then when you have a multiplication, let's say 4 times 6, you cannot make it equal to a number. You cannot make it equal to 5 because it's going to return an error message. You know? It says tag times in 4 times 6 is protected. It is telling you that the symbol in the left side is protected. That is something that has a meaning already in Wolfram language, and that's why we cannot assign the value 5 to that variable. Okay, so it means if you try to obtain that variable back here, it's not going to be equal to 5. When you press enter, it returns only 4 times 6. And then let me erase the last 2 things. So now, I told you this before, when you are representing the product of different variables using letters X, Y, Z, you need to, you can represent it like X times Y times Z, as I did it here, or you can represent it by leaving a space in between the X and the Y, another space between the Y and the Z. That if you use X, Y, Z, then without any space in between 2 contiguous variables, then it's going to understand this as a variable. So here, clear X, Y, Z. Let me clear all values of X, Y, and Z. And then if you enter the X, the Y, and the Z, you put the cursor here and you press Shift Enter, it returns what? It returns the same values, X, Y, Z. Now, if you enter new values, X equals 1, Y equals 3, Z equals 4, and you press Enter, then the X, Y, Z is going to be what? The X, Y, Z is going to be the multiplication of all these numbers. But notice that if you enter X, Y, Z, it doesn't give you anything. So the X, Y, Z, is not interpreted as a multiplication. Now, how can we enter functions in Wolfram language or Wolfram mathematics? Well, here, if you want to define a function by this formula, f of x is x to the second, you want the name of that function to be f, then you can do it like using this pattern here. So notice that we need to put an underscore after the x, This indicates that the x can be replaced by any number. And when you replace the x by any number, you have to do the same thing in the right side as we do when we are working out functions by hand. And then let me show you this example here. Well, let's enter that function. So this is going to define my function. Well, I have to clear because it is given 1 because there is an old value of y here. That's why I have to clear the value of x, not the value of y, the value of x. Okay, let me check first that this is the reason. You entered the x before and you press shift enter, it returns 1. You see that it has an old value. And then you want to eliminate that old value that is bothering here. You enter clear bracket and then the x. Sorry. Let me go back here a little bit. Then bracket, and then you press shift enter and you get nothing. Let me erase this cell for that output. We don't need it anymore. And then now when you put the cursor on top of the new input and you press enter, notice that it returns x squared. But now it works as a function, as a regular function. You can evaluate that function at any number. For example, you can evaluate it at 2, you can evaluate it at square root of 3, you can evaluate it at even at expressions like t plus 1. Well, these are 3 inputs together. I'm going to put the cursor here at the end, or you can put it at any point here of the input, at any point. It can be even in the middle here. And you press shift enter, and it returns the 3 outputs. Well, f of 2 is 2 to the second, which is 4. F of square root of 3 is 3, because square root of 3 to the second is 3. Notice that the Wolfram language is doing the simplification. It's raising the square root of 3 to the second, and it is doing the cancellation of the square root with the power. And then now here we have the 3, and for the last one, it replaces the x by t plus 1, and it finds 1 plus t to the second. Now, what happens if you don't put the underscore after the x when you are defining the function? Okay, imagine that you are clearing you clear the f. The f is representing that function, but now I define the function in a different way. I define the function like using the same expression f of x, but without putting the underscore after the x. And then what's going to be the difference here? Notice what is going to be different. If you evaluate this at 2, you evaluate this at 3, or you evaluate this at x, the only one that is going to work is the last one, because I'm telling that f of x is given by that expression. But this defines only f of x, like this expression for x, when you have an x here. But when you replace the x by any other thing, it doesn't realize that you have to replace the x by that number. And then let me enter this expression, shift enter, and then you see that it returns f of 2 because it doesn't know how to find f of 2. It returns f of 3 because it doesn't know how to find f of 3, but it returns x squared because it knows that f of x can be always replaced by x squared, because this is what this equality is telling the program. So, but this emphasizes the importance when you are defining a function, like I did it here, to put the underscore right after the x in the left side, not in the left side, not in the right side, only the left side. And then, well, when you have there is a big advantage of using names for functions, which is when you use a name for function, you every time that you are going to do a calculation with that function, you just use the function notation. That name, you have to evaluate this at a number. You define the f of x like 3x plus 1 as it is here, and later when you want to find f of 1, you enter f of 1 and it returns the value, or f of 3 and it returns the value. Then here, let me clear f, g, and h just in case there are old values before. And now we are going to define these 3 functions. F of x, notice that we have to put the underscore here after the x in the left side, is equal to 3x plus 1. G of x underscore is x to the second minus x. And the function h of x underscore is nothing more than f of x plus g of x. And then this is very convenient because if you want to find any value of h, you can do it directly using the h. The h is using this definition. Okay, let me enter the first part here. You put the cursor here, and then you press enter, and you get the two definitions. Now I define the function h by like the sum of f of x and g of x. And now I can evaluate h at any number. For example, h of 1 is equal to 1. But if you replace here the 1 by a number, let's say 3, and you press shift enter, you get the new value, which is -3 plus 2 times 3 to the second. 3 to the second is 18. 3 to the second is 9 times 2 is 18. 18 minus 3 is 15. We can also define, for example, composite function. This is the function. Again, this is a good practice. If you have to repeat the same code again and again, you have to clear every time that you need it. You have to clear all variables just in case. So we're going to clear h sub c, hc. hc is the name of this function, is the name of the function. Notice that I put the underscore here next to the x, and then I define this function like f evaluated at g of x. Okay, let me press enter here. And now, did I clear? Let me clear this again, just in case. And then I need to put the cursor here. I have to press enter, and I get this expression. Of course, the expression is indicating all the operation is not in simplified form. If you want to simplify, you can simplify that expression by doing what? By doing simplify the last output. And then the last output is represented by %. Sorry. So hit %, and then you close the bracket, you press bracket, and then you press enter, shift enter, and it gets the simplification of that expression. Now, you want to evaluate h of c at a particular number, you can do it now. So h of c at 3 is what? Is 19. You can check that this is the right result here. Now, in some different situations, it's convenient, and it is convenient also for the program to express a pure function. What is a pure function? A function for which the only thing that we have is the format. We don't have a name. For example, there are ways of expressing pure functions. For example, you want to express the pure function x, because x, when the input is x, the output is x to the second, or x is mapped into x to the second. Notice that we are talking about a function that is given just by the formula, but I'm not telling you the name of that function. And then to represent this in the system, in this program, we can use the function, the built-in function, or the built-in command, function of x comma x to the second. So this is the way of representing that function, the function that for any x, the corresponding element is going to be x to the second. This is what I'm telling you here. This is a function that transforms any x into x to the second. And then, so you press enter to enter that function. Of course, it returns the expression of the function. But you want to evaluate that function, let's say at 2, you can do it like this. You can put the 2 between brackets next to the function, and then you press shift enter, and you get the value. The value is 4. If you want to plot that function, you can put an argument t right after the formula, and to make t range from -2 to 2, and to use the function plot, which is a built-in function that we use to graph functions. And then this is going to be what? Let's press shift enter, and it graphs the function. You can also assign a name to that pure function by saying, let's say, f will be equal to function, or that function with this formula. With the formula, let's say y is equal to x squared. So, and then the name is going to be f. This is another way of assigning a name to the function. We have seen a way before. Let me go back here to where, when we did this, f evaluated at x with the underscore is going to be equal to x to the second. This is a way of saying that the function f is defined by that formula. Now, in this case, we are saying that f is the function that depends on x, whose formula is x to the second. So then when you press enter here, you are assigning that formula to the function f. And therefore now you can find values of f at any number just by doing this, using the function notation. Now, we can use replace all with functions. We are going to see a little bit more about rules later, but this is what we call a rule. For example, if you want to evaluate age of 3 in the case that the age is the function given by this expression, is the function of x that transform x into x to the second, then we can do it by using this notation. You see that you have here a slash and a dot, and then the age and an arrow. That to represent that arrow, you need to enter a dash first, and then the greater than symbol. When you do that, the system is going to transform this automatically into a little arrow like the one that you see here. Okay, but this is the way of entering this with your keyboard. Okay, it means you clear the function age, because I don't want to use any old values of age. Remember, we have to use the age before. And now you want to find age of 3, but when you replace the age by that function, then you get 9. Imagine that we change the function here, that instead of x to the second, you put x to the third. And then it means that now you need to find age of 3 when we replace the age by the function that transforms x into x to the third. So in this case, shift plus enter produces what? 27. And if you put here x to the fourth, then in this case, you are finding age of 3 in the case that age is the function, or is replaced by the function that transform any x, a function of x, that whose output is x to the fourth. So if you press shift enter here, you get now 81. Now, after using this assignment rule, where we assign the age, a certain function to age on a certain expression, actually the definition of age doesn't change with that. It means I'm assigning, this is like a temporary assignment of a certain function to age. Once you finish this, to evaluate this input, now the age becomes undefined again. So it means if you try to find age of 4, you press shift enter, you see that the result is age of 4 again. It means that it doesn't return any particular value. Why? Because this assignment worked only for this input, inside this input. And it doesn't mean that you are defining the age by that expression. But now you want to assign that formula to age, you can do it like this. Age is equal, then you need to use equal, the equal symbol. And then it's function of x, comma, x raised to 4th, bracket. And then when you press enter, You get that function assigned to age, and now when you find age evaluated at 4, you get what? Or to 3, or to 4, it's okay, to 4, you get what? You get 256, which is 4 to the 4th. Is that right? So you want to the definition to stay longer, then you need to use the equal sign. You need to make age equal this, and then to eliminate that definition, you need to clear the age. So you want to eliminate that definition, that notation for that function, the notation age for that function, you need to clear age. And once you clear the age, you can find age of any number, let's say age of 6, and you're going to see that it returns age of 6 because there is no there is no a defined expression for age. Now, another way of expressing pure functions, which is similar to the one that we saw before, like this one here, is the following. Instead of entering x and then the formula in terms of x, we can just put the formula, but the formula must be written like this, using the number symbol here, the symbol for number to the second. And then when you enter this in this way, this is the function, the same function that we have before. The only thing that this notation is shorter. It means we have function. This is the function whose formula is, it takes a number, the input, and raise it to the second. It means if you apply that function to 3, what do you obtain? You obtain 9. If you want to plot that function, what do you have to do? You have to evaluate that function at x and to take all values of x from -2 to 2. This is the way of indicating that, and to use plot. So later we're going to see the form of the plot function in more detail. Okay, but that function that is expressed in that way using the symbol of number, or the pound symbol, it can be expressed also in an even shorter way by putting the number symbol raised to the second and this symbol, and then when you evaluate this at 4, you get the 4 to the second. And then if you ask whether this function is equal to this function, notice that I know that I'm asking here because this becomes a logical statement when you put the double equal sign in between. So you put the symbol, the cursor at any point on that input, you press Shift Enter, and it returns true. It means that this is the same function as this one. And both are equal to the function that turns x into x to the 6. Okay, now, inverse function of a function. Well, there is a function, a built-in function in Wolfram Mathematica, or Wolfram Language, which is called inverse function, that allows us to find the formula for the inverse function of a function whenever that formula exists. For example, we are going to start here. Well, let me tell you something. If you want to know more about that function, about this built-in function, and you can do the same thing with any built-in function, you enter a question mark and then the name of the function, the Wolfram Language function, and then you press Shift Enter, and you get the syntaxis of that function. You see the explanation, how the formula, how the function can be written here. So inverse function of a function f represent the inverse of f. And so define so that inverse function of f evaluated in y give the value of x for which f of x is equal to y. So it defines the inverse function. And then it says inverse function of f, n, tot represent the inverse with respect to the nth argument. When a function has more than one argument, you can find the inverse just with respect to one argument. And when this is the total number, the tot is the total number of arguments. Well, this is more advanced. We are not going to see any situation like this. So then we're going to start here to see some examples. We're going to clear the F. We are going to enter this function. The function has this formula. And now we can find the inverse of that function by using this Wolfram Language function. Inverse function, and then the F between brackets, and then the X between brackets. You press enter, and it returns the formula for the inverse function. What about we eliminate the X from here? If we eliminate the X from here, it returns what? It returns the formula, the same formula, but now as a function without a name. This is the function that when you evaluate this at X, it does this. It adds -1 plus 3 times the X and divides by -1 plus 2 times the X. So it means the numeral symbol here represents the position of the X in the formula. And this always represents that this is a function with that formula. Okay, well, in this case, if you want to see a nicer expression, you put the X at the end, and then you press Shift Enter, and it returns the formula for the inverse function. Now, if you want to evaluate that inverse function at any number, you can do it like this. Let me show you an example. Inverse function, let's say at 4 is what? Sorry, I forgot to put the F. Inverse function of F at 4. Go back a little bit. Bracket, 4 bracket. And then it returns 11/7. Now, if you evaluate the original function at 11/7, what you should get, 11/7, you should get what? You should get the number 4 back. You get back, the number 4 back. And now, if you want to find the composite function of the inverse function of F with the F, you can do it like this. You evaluate F at X and then the inverse function at F of X. What do you get? Well, let's see what we get here. You get this expression, but of course, this expression, if they are inverse of each other, this expression must reduce to X. In this case, they are not giving you the final value. That you need to use a command here to simplify that. For example, simplify. And then you put that expression between brackets. You can copy and paste. You click here and you copy to the clipboard, and then you enter that expression here. Or you can use a name for that also. You name this, let's say, the expression EXP5, and then you use here simplify EXP5. Now here, if you press enter, you get X. It means that after simplifying the whole expression here, the expression that you get is X. Now, another example, we can find the inverse function of a function which is a pure function. This is the function whose formula is X times e raised to the X. The number e is represented by capital letter E in Wolfram language. So, and then, well, now let us find the inverse of that function. That function, the inverse is not possible to find it by hand, but this function has a name. It's the product log function, the product log of any number. You know, this is going to be the inverse function product log is by definition one of the inverses of this function. It is it has more than one possible inverse, but this is one of them. Then another example here, you evaluate the inverse function at 3, you get what? The inverse function of that function of x times e raised to x. Evaluated at 3, you get product log of 3. Well, it doesn't tell you too much because you don't know what the product log of 3 is, but you can get an approximate value using the function n. So here, you press enter, you get what? You get 1.04991. Okay? So this is going to be the approximate value of that number. And now we can graph the inverse function of that function by using plot here. So is plot the inverse function of x times e to the x evaluated at x when the x goes from -3 to 3. Let's do the operation here by pressing Shift Enter. And we get the graph of this function. And you can see that it looks like a logarithm. It starts here, it doesn't go down forever, but the shape is, that's why they call it the product logarithm. Well, actually, implicit functions. We can also graph implicit functions. I mean, first we can deal with implicit functions. What is an implicit functions are defined by implicit equations. And then, so in this notebook here, we're going to focus on implicit equations of the form of this form. F of x comma y of 0. F of x comma y is equal to 0. So a function f of x is an implicit function defined by the implicit equation, by this implicit equation, if when you replace the y by that expression, f of x comma small f of x parentheses is equal to 0, it's going to be equal to 0 for all values of x in a certain interval. Given an implicit equation, we can use solve to find a corresponding implicit solution. Given implicit equation, x to the second plus y to the second is equal to 4. Find the function f of x that is defined by the implicit equation. One of the functions that is defined by the implicit equation. Find for that function, find f of 1, f of 0, f of 0.5, f of 3. Verify that the equation becomes an identity when you substitute the y by f of x. As we mentioned here, that f evaluated at x comma f of x must be always equal to 0 for all values of x in a certain interval. And then let's graph the function f of x. Well, to find a possible function f of x, we can use the Wolfram Language function solve. Then we are going to use the name of the f as the name of a certain function. That's why we are going to start to clear. Even if we haven't used this before, it is important to clear the value, because if you repeat the use of this part of the program again and again, and you can obtain a certain definition for the function f, and when you repeat the calculations, the program can be using that old definition. So it is good. It is a good practice to start clearing all the variables that we're going to be using here. Then now we are going to define a function of two variables, function of x and y, defined by this formula. It's going to be defined by the formula x to the second plus y to the second minus 4. So let me put the cursor here to press Shift Enter, and we get, you see, there is a problem with the y. The y was 0 at some point before. That's why it's not appearing here. That's why here we need to clear not only the f, but the x and the y also. The x and the y. And then you press Enter. And now let me repeat to run this input again. So here you press Enter and you get what? Now you get the whole expression of that function. Now I'm going to represent, I can solve this equation for y. I can solve this equation for y. To solve this equation for y, I use the built-in function solve. So solve that equation, f of x comma y, double equal sign for any equation. Whenever you are using an equation, in this case, we are assigning this expression to the left side expression. So as it is an assignment here, we use only one equal sign. But whenever you consider this as an equation that eventually can be something that is true or false, we use a double equal sign. And then we are going to solve this for y, and the expression that we get, we are going to call it S-solve. So you press enter. And notice that S-solve represents these two solutions. These are two solutions of the given equation when you make it 0. Okay, the y can be -4 minus x squared, or the y can be a square root of 4 minus x squared. So this is a list, and this is a list of rules. The first rule says that whenever there is a y, you can replace it by this expression. The second part of the rule here, the second rule here says that whenever you have a y, you can replace it by the square root of 4 minus x squared. And then if you want to get only the first rule, you can do it like this. For the list, you find the first element, which is represented like the first one here. And for that first element, you take what is inside the braces. It means the first element of the list, which is represented by these braces, which is represented by the second one that appear here. It means that when you do that, you get this expression. You get the expression, the first expression here, the y. This is a rule that whenever there is a y, it replaces the y by minus a square root of 4 minus x squared. And now you can clear the function f. We're going to define a function f for this variable here using this variable. How can we do it? Well, we clear the name f because we are going to use it now, and we define a new function f of x underscore is equal to the y, where that y is obtained by applying this rule. And the rule says that the y is replaced by what? By minus square root of 4 minus x squared. This y must be replaced by that, only at this moment here. It means we press Shift Enter, and you get the expression for that function. Now you can evaluate that. This is a possible solution of that implicit equation. Now, if you want to find some values of f of x given by that equation, you can check it by doing, let's say, f of 1 or f of 0, f of 0.5, f of 3. When you press enter here, you get what? F of 1 is what? F of 1 is minus square root of 3. Is that right? When you replace the x here by 1, 1 to the second is 1, 4 minus 1 is 3, you get minus square root of 3. When you replace the x by 0, 4 minus 0 to the second is 4, the square root of 4 is 2, and then you get minus 2. When you replace the x by 0.5 in that expression, you get minus 1.93649. And when you replace the x by 3, notice that you get 4 minus 3 squared, which is 4 minus 9, which is -5. And then you get a complex number. Notice that in this case, it produces minus I times square root of 5. Now, if you want to verify that f evaluated at x, comma, f of x, when you replace the y by that expression that we obtained before, that this is always identically equal to 0, you can do it like this. You evaluate f, you enter x, comma, and then you replace the y by f of x, and let's see what happened. And you put the double equal sign here. So let's see what happened. It says that it's true. Why? Because it does the calculation into the formula, And it means that in this formula here, x to the second plus y x to the second is equal to 4. It replaces the y by one of these two expressions that we obtain when we solve for y, by the first one in this case. And when it does the simplification in the left side, it gets 4 is equal to 4. So, well, in this case, the 4 is to the left side. It has been moved to the left side. And we have 0 on the right side, but it gets 0 is equal to 0. And that's why we get that this is true. Now, let us graph the function f of x. Well, what do you have to do? You have to plot f of x on the interval from -3 to 3. This is the function that we have to use. Okay, then, so let's press Shift Enter. Notice that this is the graph. But actually, if you see the original equation of that curve, you see that this is the equation of a circle. Why the result here doesn't look like a semicircle? Doesn't look like a semicircle because notice that the distance from here to here is 2 units on the x-axis, and the distance from here to here is 2 units on the y-axis. So it means that the scales are different. And then to make the scales equal, you will need to use the following option for the function plot, which is aspect ratio. You make it automatic, aspect ratio, and then remember to enter that this arrow here. You do it by entering the dash and then the greater than, and then it automatically turns this into a little arrow. And now when you press enter here, what do you get? You get the same graph, but now the scales are the same for both the x and the y-axis, and that's why the shape of the circle is more evident in this case. Now we are going to, the next example is given the implicit equation x to the third plus y to the third minus 9xy is equal to 0. Find a function f of x that is defined by the implicit equation. Find the values f of 1 and f of 0, f of 0.5, f of 3. Verify that the equation becomes an identity when you substitute the y by f of x. Graph f of x. And then we're going to start clearing the function f as we did it before, and clearing the x and the y. Remember, we use semicolon here when we want to put many inputs, one in a row, but the outputs, but I want that the only output that appears here is going to be the output correspond to the last input. So it means I'm going to clear f, I'm going to clear the x and the y, semicolon, semicolon, and then I'm going to make the f of x comma y equal to this expression. Notice that we use underscore here and here because this is going to be a function of two variables. And then I want the x and the y to be replaceable by any number or any other expression. So that's why I put the cursor here, I press enter. And this is going to be the expression of the function. Now I'm going to clear another variable that we're going to use here, just in case if I have to use this part of the program many times. Every time that I go here, I go to the top, I want to clear this. And then now I'm going to solve this equation for the y. I'm going to solve this equation, the previous equation. When you make it equal to 0, this expression, you make it equal to 0 using a double equal, you get an equation, and then you're going to solve it for y. And when you solve it for y, you're going to put the whole list of solution here. Then we're going to denote it by this name as solve. And so I put the cursor there, I press enter, and this is going to be the list of possible solutions. If you count here carefully, you see that there are three rules. The y can be replaced by this expression, the y can be replaced by this other expression, and for the last part, the y can be replaced by the last expression here. So basically, we have three functions here that we can obtain correspond to this implicit equation. Now we are going to introduce a name for the one that we're going to use. We're going to use the first one here, the first solution. And then we are going to use that one to define the function f. Or we are going to denote this one with the name f. So I'm going to clear the f, and I'm going to define f evaluated at x underscore is equal to the expression y, where we use this rule. And then here, remember, S sol represents the whole list of all the rules. When we put the 1,1 here, we are talking about the first rule only. And then when you press enter, let me check it. When you press shift enter, you get that this is the expression. You see that it coincides with the expression that appears here in the first rule of replacement. And then now, using that expression, we can use it to find different values. Like, for example, to find the values at 1, 0.5, 3. And then when you press shift enter, you get some values here. You get some values. If you want to find the numerical values of those values, you can use the n. You can put the function n affecting any one of these values. So here n, and then the whole expression in between brackets, and then n, the whole expression between brackets, and now look at this. In this case, it is saying that f of 1 is this value. Notice that this value here is 2 point something times 10 raised to negative 16. This is a very small number, and this is telling you that the imaginary part. The problem is that the computer is calculating the values approximately, and then the imaginary part here is very close to 0. That's why you can consider this to be 0. In this case, it tells you that the imaginary part is 0 because it's 0 times I. And in this case, it's also a number very close to 0. So it means that basically the numbers that count here are the real parts only. The real parts. These are real numbers, but the problem is that the program is using a method that considers possible complex solutions, and is finding the approximate values of those real numbers in the set of complex numbers. And then in this case, these are going to be very good approximations, but these are complex numbers. But for them, the imaginary part is very, very small. So you can eliminate that imaginary part. And then, so here, you can simplify. Let's see what happens when you apply full simplify to the last two numbers. It means you get, when you apply full simplify to those numbers, you get a simplification of the values that we had before. Okay, for example, for f of 1 without the n, when you find f of 1, you get this expression. But you see, this is an expression that at least formally contains imaginary numbers. Actually, this expression, when you do the simplification, the imaginary numbers disappear, you know. But as the calculator, I mean, the computer is doing this in an approximate way, that's why you got a very small imaginary part. But then this is the first number here. If you want to find an approximate value of this, after full simplifying an approximate value, you get you need to put the n outside, and then what do you get? You see, you get the approximate value here. Let's full simplify and get the approximate value. Let's put the n for this one also. And then anyway, you get the 0 times 5 times I. And for the last one, when you full simplify, you get even the exact value. But if you want to get an approximate value, what do you have to do? You need to put the function n in front of that, affecting the whole thing. And then you get the approximate value for that expression. You see that, and the approximate value is 4.59627, which is what I did here. So we don't have to repeat it. And then let us simplify. Oh, well, let's verify that f evaluated at x, and when you replace the y by f of x, is always equal to 0. What do you have to do? In this case, you know that the f of x comma y is the original expression which is given at the beginning. This is my f of x comma y, x to the third plus y to the third minus 9xy. Notice that we have left the spaces here in between the x and the y, the space. And then, so here, when you press enter, in this case, the expression of the left side is very complicated. That's why it doesn't simplify here automatically unless you tell the program to simplify that. And that's why it doesn't answer whether this is true or false. But now you can use simplify. Remember, the percent denotes the last output, which is the whole equation as it is written here with a double equal sign here. And now it's simplify, you press enter, and you get true. It means that after simplifying the left side, the program finds out that the left side is equal to 0. And now let's plot the function f of x. Now you can do it like this. Then you press shift enter. And this is going to be the shape of the function. The function looks like this. Notice that this function has a corner at 0, 0. And this is possible. Why? Because remember that corners are related to function with radicals. Okay, and these functions contain radical. And the expression of that function, the function f of x, which is the function that we define here by this expression, it contains radicals. And then when you find the derivative, the corners can appear. Now we're going to move to the next topic, which is about rules. A rule, a replacement rule, always has the form LHS, or left side becomes, is replaced by the right side expression. The left side expression is replaced by the right side expression. So it means the rule replaces LHS by RHS. Okay, remember that to enter the arrow, you have to press the key for the dash, which is on the top of the keyboard to the right, and then the combinations of letters, of keys for the greater than. And in that way, you get, automatically you get the arrow. Okay, you can use rules to evaluate formulas at certain values of one variable. For example, here, you have an expression x to the second plus 3x plus 2. And for that expression, you want to evaluate the x at 3 and to see what do you get. Well, one of the advantages of doing this, using a rule of replacement to do that, is that you are not making you make the x equal to 3 only at that moment. But later, the x is again, it doesn't have any value again. So you press enter, you get what? You get 20. And then this means that the x to the second, 3 to the second is 9, plus 3 times 3 is 9 plus 9 is 18, plus 2 is 20. You get 20. Now, as I was telling you, if you enter the x again and you press enter, you see that there is no value for the x. There is no value for the x. Now, the rules can be also inside braces, because you can apply, you can do a list, you can use a list of rules applied to an expression at the same time. That's why it does make sense to have a list of rules here, but this list in this case have only one rule. So if you apply this to the same expression, you get the same result again. But when you have, I mean, this is what I was telling you. When you have an expression that depends on many variables, x, y, and z, and you apply a list of rules of replacement, replacing the x by 1, the y by 2, and the z by 3, they do all the replacements at once. All these are the replacements at once. So they replace in that expression the x by 1, the y by 2, the z by 3, and you get what? You get the resulting value here. If you check this by hand, you see that this is what you get. You replace the x here by 1, the x by 1 and the y by 2 here, and the z by 3 here, you end up with this value. And again, notice that after the application of this rule, the values of x and y, they don't change. In some cases, what happened with the value of z? Well, actually, we have a value of z from before. Let me see. We had a value, but it doesn't matter. Even if there was a value of z before that, it's not going to affect this. When it does this calculation, it replaces the z by 3. It means before that, let me see. So here, if you enter the z and you press enter, it returns 4 because we had a value of z from before that we didn't erase. You want to erase it before doing these calculations, then you enter clear z, and then you put the cursor, on that input. On top of the input, you press enter, you clear the z. Now, if you enter the z now, and you press shift enter, you get no values. You get no value. Let me erase these cells here, correspond to this out. And now let's do this again. We are going to evaluate that function when the x is replaced by 1, the y by 2, the z by 3. You press enter, you get, you get 14. You see, it does affect. I was telling you that doesn't affect, but it does affect because the system was, and that's why you need to be clear. You need to be very careful with clearing all the variables that you are using, because if you have used that variable before and it had a value, even when you apply a rule here, it takes the old value and not the new value. You understand what I mean? That's why here you get a different value, which is 14. Now, when you enter the x, the y, and the z, you get what? You get x, y, and z. It means that now the z, after applying the rule, the z is again a variable with no value. A variable with no value. We can also use rules to replace not only variable, but to replace whole expressions, or in a given expression, a given algebraic expression. For example, you have that t is equal to x raised to the third plus x raised to the second plus 5x plus 7. And then this symbol, the slash and the dot, means that you are going to replace all according to this rule. Whenever the expression x to the third appears, you're going to replace it by 1. Whenever the x to the second appears, you're going to replace it by 2. And whenever the x appears, you're going to replace it by 3. And then what do you get now? You get 25. When you replace the x to the third by 1, you get 1 here. Plus 2 is 2. 5 times 3 is 15. So 1 plus 2 is 3 plus 15 is 18. 18 plus 7 is 25. And this is going to be the result. Now, the t does maintain its value beyond this input. Okay, the x and the y, if you evaluate the x, the y, and the x or the x to the third or x to the second, before, after that, they are not going to have any values. But the t, why? Because we have used the equal sign here. Whatever the value we obtain here on the right side is assigned to the letter t, because this is what the equal sign means. And therefore, when you press here, shift enter here, putting the cursor next to the t, you get 25. Now, you want to eliminate the value of t, you need to clear the t here. And now, if you enter the t again, and you press shift enter, you get t, meaning that it doesn't have any value. Now, when you enter a list of substitutions like this, where you are replacing the same variable x by different values, by 1 here and by 2 here, what do you get in that case? You want to evaluate that expression, x to the second plus 1, but when the x is 1 and when the x is 2. What do you get in this case? You get a list of the values. A list of values, the value at 1 and then the value at 2. Let's press shift enter. And then you say that the value of that expression at 1 is 2. When you replace the x by 1, 1 to the second is 1 plus 1 is 2. When you replace it by 2, 2 to the second is 4 plus 1 is 5. And you get a list of values. You can also use rules to replace a function by another function. Let's say if you find the sign of pi over 2, the number pi is represented by this letter. We never use all the functions. Notice that all functions, all the Wolfram language functions, all the Wolfram mathematical functions, the name of them, all the built-in functions, they always start with the capital letter, and the argument is always in between braces. If you enter sine of pi divided by 2, and notice the way that we enter pi in this program. Pi is a capital letter, p and the I, a lowercase letter I. If you press enter here, you get the sine of pi over 2, which is 1. But if you have an expression like this, you might want to replace the function that is evaluated at pi over 2. How can you do that? You can do it by means of this rule of substitution, of replacement. So it means you have the expression sine of pi over 2, and then this symbol means you replace the sine by what? By the function that, the pure function that converts x into x to the second. So it means that basically what you're going to obtain, instead of obtaining sine of pi over 2, which is 1, you're going to obtain pi over 2 to the second. So here you press enter. And this is wrong for some reason. Sorry. Let me see what is happening here, why this is not working. Let me see, the x. What is the value of x? There is no problem with the x. But you have an expression like this, well, it seems that this doesn't work. Let me see if it works when I have cosine here. Cosine, if you replace sine by cosine, no, it doesn't work in this case. It doesn't work. Well, of course, if you had a name, because it calculates first, the problem is that it calculates first the sine of pi over 2, and then you have already found that value. And then when you replace sine by cosine, you already have a value here. So let me put it in this way. Let's say, let me call this f. Let me clear the f before that. So we're going to clear f. And then you press shift enter, you have cleared the f. And then we are going to put the f, but I don't have any expression for the f. But now I'm going to replace, to calculate that expression, when I replace the f by cosine. And then you press shift enter and you get what? you get 0, because when you replace the f by cosine, you are obtaining cosine of, well, the program cannot calculate this at the beginning because this is an f which is not defined. It's a function that haven't been defined. And then, but when you replace the f by cosine, you get the value. This is cosine of pi over 2, which is 0. Now, solving equations. Remember, we use the symbol equal, only one equal, to assign a value or an expression to a variable or to another expression. Let's say when you say x is equal to y over 3, y raised to the third, then let's do this to see what happens. You are assigning y to the third to that variable x. It means you are using the symbol x to represent y to the third. And this can be important when you want to represent complicated expression with simpler symbols. And now, if you calculate the x plus 1, what do you get? You get 1 plus y to the third. And now, you can clear that definition of x by clearing the x. Okay? Now, the double equal sign, it is used like for equations, basically. And then when the left expression is double equal to the right expression, it always returns true if the two expressions are identical or equal, and then it returns false, or it doesn't return anything if they are not equal. Let's see some example. For example, we can here 2 times 3. This is like asking the system, is 2 times 3 equal to 6? What is going to be the answer? Well, let's press Shift Enter here. The answer is true. When I ask the system, is x plus 1 equals x plus 1? You press Shift Enter. What is the answer? True. When I put x plus 1 in the left side and x plus 2 in the right side, and I press Enter, it doesn't return anything. Well, in this case, it returns the expression for dx. Dx is a y to the third, and then 1 plus, it returns the same equation again. But in this case, replacing the x by the y to the third. Of course, if you clear the dx again here, if you clear dx, then when you enter this expression and you press Shift Enter, it returns what? It returns the same equation, but it doesn't tell you whether this is true or false. Now, it means we always use the double equal to represent equations. For example, x to the second plus 2 is double equal, and we use the double equal sign, 3x, and then this is an equation. We can just enter that equation, but it returns the same equation because there is no value for dx here, so there is no way of saying whether this is true or false. But now, if I want to solve this equation with respect to dx, I can do it using this command. So solve the equation, comma x, it means with respect to x, you press Enter, and it returns the two solutions, again, using the rules. It means the first rule here assigns to x the value 1, the second rule assigns to the x the value of 2. Then if you want to represent the list of these two rules, you can assign a name to solve from the beginning. You can do the same. Okay, and then you press Enter. You don't get anything because, oh well, you get the expression of soluk. But then if you apply these rules to the equation, you have the equation. If you apply this rule to the equation, you need to write down here a dash, then the dot, and then the list of rules. When you apply these rules to this equation, what the system does is to replace the x by 1 and by 2 separately and check whether the resulting equations are true or both or not. And then here, when you press Enter here, you get what? You get true and true. It means that both are solutions of that equation. So this can be a very useful way of checking that the two functions are solutions of that equation. The two values, the two numbers, are solutions of that equation. Now, graphing functions of one variable. This is another important part that we need in differential equations to be able to graph functions of one variable or implicit functions. Also, we're going to see both here, both topics. So here, how can we remember that I have told you before, this has appeared before, that the command to graph a function of one variable, it can be expressed in this way. Plot, remember, any Wolfram Language function starts with a capital letter, and then in between brackets here you have the f of x, f of the x is also between brackets, and then when in between braces here, the x goes from a to b. So you want to plot the sign of x in between negative, let's say, pi and 2 pi, you get what? You press Shift Enter, and you get the graph of this function between negative pi and 2 pi. And now notice that we use the symbol here, pi, with a capital letter to represent the number pi. And we can get approximate values of pi using the function n, as we have done it before. So here, n of pi is what? You press Shift Enter, and you get an approximate value here. In this case, this is rounded to 5 decimal places. But you want to obtain a better approximation, you enter the function n of pi, and then to 20 decimal places. So you press Enter, and you get an approximate value to 20 decimal places. You want 200 decimal places, you can also get an approximation to 200 decimal places. Okay, this is going to be you can count the numbers here. They are going to be 200 decimal places here. Okay, well, now you can plot more than one functions using this command. Notice that in this case, we are going to write down the function. When we have only one function, we write down the function and that's it. When we have many functions, we can enter them as a list of functions. So it means this is a list of functions. For example, you want to graph the sine and cosine together. You enter plot, bracket, and then we have the bracket closes here. But then you put the two functions, sine of x and cosine of x, between braces, because it's a list of functions. And then where the x go from negative pi I to 2 pi, and then you press Shift Enter here, you put the cursor at some point on top of that input, and then you press Enter, and you get the two graphs. You know, if you remember trigonometry, you know that the blue one is the sine, because it passes through 0, 0. You know, when the x is 0, the y is 0. It passes through 2 pi comma 0, it passes through pi comma 0. The yellow one is cosine. But we can use a legend here to see which one is the sine, which one is the cosine. And then automatically the program is going to label them. So if you enter plot sine of x, cosine of x, and you put this option at the end, plot legends, expressions, and then you press Shift Enter, you get this. You get this, and you get a legend here. The blue one is the sine, the yellow one is the cosine. Or you can also put, the name of the function next to each one of the graph. Not to use a legend, but to put the name of the function next to each one of the graphs. So when you press Shift Enter here, you get this. The yellow one is the cosine, the blue one is the sine. So another option for graphing function is plot range. The plot range specifies the range of the y coordinates. Here it must say y coordinates. Well, in some cases, the coordinates, but in this case, only the y coordinates. In some other cases, we can use the range to express the range of each one of the coordinates, but in this case, it's going to be the range of only of the y coordinate, and then to include in the plot. In general, this option is used with the plot to specify the range of the y coordinates. Coordinates, actually, yes. In this case, we use, we have a little space here. We use the following settings: the plot range, and then a dash, the greater than for the arrow to the right arrow, and then the y minimum, the y maximum. For example, for the graph before, you can use, you can graph sine of x and cosine of x on the interval from -pi to 2 pi, and then we are going to plot labels are going to be expressions. So it means we're going to label both graphs, and the plot range now was -2 and 2. It means the y minimum is going to be -2, the y maximum is going to be 2. Notice that in the original graph here, it chooses the plot range automatically here. It chooses the smallest possible plot range. In this case, it goes from -1.2 to 1.2 approximately. But then here, let's see that my range, the range of the function, the part of the the interval for that goes from y minimum to y maximum, in this case, is going to be different. Let's check it. Let's see. You see now, notice that the graph now looks smaller, and then this number here is -2, this number here is 2. Now, let's see how can we graph lists of functions. You can graph a family of functions in the following way. Let us generate a list of functions in the following way. Well, so there is a repetition here. So in this case, so here, we are going to define the following list of functions. The functions are of the form a times x to the second plus b, where we replace, remember this symbol means that we are going to replace all, it's called replace all. And we are going to replace the values of b by all the values in this list. And then we are going to replace the values of a by all the values in this list. And then when we do that, we get a list of many different functions. This is the list of lists of functions. Now, if you plot, you want to graph all the elements of those lists, all the functions, you can do it like this. Put in plot, and then you put here list of functions, which is the name of that we assign to this list. And then we are going to plot it. And then we get this nice graph with all the functions. This is very convenient when you are representing elements of a list, of a family of functions, of a family of solution of a differential equation. We want to represent some of those solutions of the family of solutions. We can do it like this. We can also graph implicit functions or implicit equations. Graphing implicit equations. Well, we can graph implicit functions which are defined by implicit equations. Later, we're going to see that we can graph implicit equations also. Well, to graph implicit function defined by an equation of the form f of x, y equals 0, we use, instead of using plot, we use contour plot. Contour plot, and this is the syntaxis of this command. It looks like this. Notice that contour plot, the C has to be written with a capital letter, the P with a capital letter, and then in between the braces here, in between the brackets that start here and ends here, we have first the equation with double equal sign, and then the x go from a certain number x minimum to a number x maximum, the y goes from y minimum to y maximum. And then, for example, this is a known implicit equation whose curve is called the volume of this of the cards. And then you want to represent the whole equation, you use contour plot. And then notice that we entered the equation x to the third plus y to the third minus 9xy double equal sign 0. And then the interval for the values of x, the interval for the values of y. And then we are going to use this option, axis true, to specify that we want the graph to show the axis, the x-axis and the y-axis. So here you press enter, and you see this is the volume of the cards, which is the graph of that function. Before, we saw that this implicit equation define one of the, we obtain one of the explicit function defined by this implicit equation, and the graph was this part of the graph, this part going to 0, and then instead of continuing over here, it continue going through this part here and ended approximately over here. So actually this was the expression that we found for that function. And then if you use plot, notice that now we don't use, no longer use contour plot, but plot. And then you press enter, you get this part of that curve. You see, you go back, you can compare what part of the curve is given by this formula. Now we can also graph lists of implicit functions. To graph a list of implicit functions depending on one parameter. For example, graph these implicit equations for the following values of c. When the c is -10, -6, -2, 0, 2, 6, 10. First, we are going to start clearing this name list of equations. I haven't used that yet, but it is important to always clear this every time that we run this part of the code, because if we go down and we want to start again, we want to make sure that we don't have that, we don't have a value for that variable, which is list of equations. So we press here shift enter, and now we are going to define the list of equations like this. The equations are going to be x to the third plus y to the third minus 9xy equals a constant c. Notice that we use the double equal sign here because it's an equation, but where we replace the c by these values, -10, -6, -2, 0, 2, 6, 10. And then we press enter, and we get that in the left side we have that expression, in the right side we have the list of possible values. Okay. Notice that well, if you enter this directly here in contour plot, then this is not going to work. You press shift enter, it doesn't produce anything. Why? Because sometimes for contour plot and sometimes for plot also, we have to include a function here for this to work, which is evaluate. Because there is a problem with the evaluation, with the order of the evaluations. Those function plot and contour plot, they have an attribute, a characteristic or an attribute which is called hold all, that postpone some evaluations, and then in this case it doesn't work very well for us. But if you use evaluate, this is going to do all these evaluations before when is needed, and then it is going to be able to graph it. And then you see this is all the graphs correspond to those constants. The constants -10, -6, -2, 0, 2, 6, 10 in the right side. Now we are going to move to the topic, the section about derivatives of a function. Derivatives of a function. And we're going to see here different ways of calculating derivative of function and expressing them. in this program. As I have told you before, it is a good practice to start clearing the f, because we're going to use f as the name of a function here. Clear f, and then we're going to define f. Let me put the the cursor here and shift enter. Now we are going to introduce a new expression for that function f of x. Remember, we need to put the underscore f of x underscore. And now when you put the cursor here and you press shift enter, this is the expression of that function. And then now what is the derivative? You can find the derivative just by using this notation, which is very similar to the notation we use in mathematics. You press enter and you get that this is a new function whose expression is exactly the derivative of this polynomial. Okay, you can check that. -1 is the derivative of minus x. Well, the derivative of 7 is 0. -1 is the derivative of minus x. 10x is the derivative of 5x squared. And 3x squared is the derivative of x to the third. And then you can evaluate now this derivative at any number. For example, f prime of 2. Let's do it. And then you can graph the function, the derivative. So the only thing that you need to do is plot the derivative from -3 to 3. And you get that this is the graph of that derivative. You can graph both together, both functions together. We can graph the function f of x, that is the original function, and f prime. Notice that now we have to put the two functions separated by commas and in between braces. And we're going to plot, to use labels for both functions, for the both graphs. So you press here, shift enter, and then you get that the blue one is the graph of f of x, the yellow one is the graph of f prime of x. Now, another way of calculating the derivative of a function is by using this symbol, d, or a big D of f of x comma x. Well, you can do it here. We already know that f of x is that expression. We haven't cleared this again. So you press here, shift enter, and you get the expression. But now, if you want to evaluate this at a number, at a certain number, then this option here doesn't work. If you put the number in between two brackets, in between the left and the right bracket, and you press enter, this is not going to work. It doesn't do anything. But what do you have to do here? You need to apply, you need to use a replacement by a rule. What is going to be? The rule can be expressed like this: x and then slash greater than, and then you get the arrow, and then you put the 2. So it means that in that expression, you replace the x by 2. When you press enter, you get the value, which in this case is 31. Now, if I ask you, you see that this is a shortcut, because everything in Wolfram language is an expression. The g prime of x is a shortcut, a shorthand notation for the derivative, but there should be an expression for that has a head, and if you want to find the full form of that, you can enter full form g prime of x, and now you press enter, you get what? Well, the problem is that I have used the g before. Let me clear the g. So you press shift enter, and then full form. Then you see that the full form of this expression is, you put a 1, the first place here, in between brackets, then the g between brackets, and then the x between brackets. Okay? And then this is telling you that you are finding the first derivative of g. The 1 means first derivative of g, with respect to x. With respect to x. And then for our function f, what is going to be the first derivative of f with respect to x? When you press enter, you get that expression. Now you can evaluate at any other number, replacing the x by any other number, you get what? This is a good thing about using this formula. You get the value. Okay. Now you can also find, let's say, the second derivative using the f double prime at x. You see that this is the second derivative of that polynomial that we introduced before. And also you can use this other notation, which is derivative 2 between brackets and then f between brackets evaluated at x. So this is going to be the same expression. We can also find second derivative using the other expression, which is repeating the x here. Well, it's second derivative. You need to, if you are finding the first derivative, you put the x only once. If you find the second derivative, you need to repeat the x twice. And then in this case, you get the expression for the second derivative. But if you don't want to repeat, it means you have to find the fifth derivative. You need to replace the x 5 times. But if you don't want to do this, of course, you can use this format. Rather than using this format, you can use this format here. You find the derivative of f of x, I mean d of f of x, comma, and then in between braces, you put the x and the number of times that you want to differentiate this. So it means that in this case, you get the same thing. And then remember, you can evaluate an expression like this or an expression like this at any value of x just by writing down the value of x. In this case, the second derivative of f at 2 is 22, and the second derivative using the other notation is 22. But you cannot do the same thing here. In this case, you need to use a rule, a replacement rule. Okay, you need to use replace all and then a replacement rule. When this case is you find the second derivative and then you replace the x by 2 in that expression. So, or you can do it like this, which is the same. Well, let's see that the result is the same in both cases. And then remember that the derivative, this is the nth derivative of y. When you press enter, you get nth derivative of y. Notice that the n appears here in between parentheses. That indicates that this is the order of the derivative, not an exponent. Not an exponent. Now we are going to see the examples of differential equations where some simple example of differential equation for which we can use well, Wolfram language to solve them and to represent the solutions graphically and to find values of the solution. So remember that the general form of the differential equation of order n is this: f that depends on x, y of x, y prime of x, all the way to the nth derivative of y with respect to x is equal to 0. When the order is n equals 1, then we can represent a differential of first order in the general form: f that depends on x, y of x, y prime of x is equal to 0. If you can solve it for y prime of x, then we can write down the last equation in this form: f y prime of x in the left side, and then an expression that depends on x and y in the right side. And then well, we can enter the dy dx minus y equals 0 in this program like this. You can enter the equation like this: y prime of x minus y of x double equals sine x. And then you know that the general solution of that equation is a constant times e to the x, where the constant c1 is whatever real number. And then let's enter this function. Let me clear the function f and to define the function f by this expression, the expression that we have here. Okay, this expression. Then you put the cursor there, you press shift enter, and then this is going to be your function. Notice that when you enter C, capital letter C or 1, it writes down like this, like a boldface letter C sub 1. And this represents a constant. Then if you want to verify that this equation is satisfied by that function, we can do the following. We write down the equation as we did it here with the double equal sign and everything, and then in that equation we replace the y by the function f. It is telling the program that whenever the y appears, you need to replace it by the function f. And then what do we get here? We get a true statement, meaning that when you replace the y by that function f, this function satisfies the equation. Another example, in this case, a function which is not a solution, for you to see what happened in this case. If we define another function here, let me clear the g before we do it, because we might have used this before. Clear the g, and then you press enter. We have cleared the g. Now we define g like this expression. G is e raised to 2x times a constant c1. And now we are going to, in our equation, we are going to replace the y by the new function g. This function is not a solution of that equation. You can do it by hand and you can check it. Now, when you press shift enter here, what do you get? You get e raised to 2x in the right side, in the left side, times c1, and is and double equal sign and the 0. This means that this is not a solution. Of course, it's not a solution unless the c1 is identically equal to 0. This is the only case when this is going to be a solution of that equation. So it means this tells us that in general, for whatever value of c1, this is not going to be a solution. And then, well, we are going to clear now the f and the g here, just in case if we use them afterwards. Now, we are going to see an example where we solve a first order differential equation. And I want to pay attention to this because this is what I'm going to ask you to do in your project, to do something similar to what I'm doing here and what I did in the previous example. So to solve a first order differential equation, we use this solve. Then the equation, we use this command, this solve. And then you write down the equation and then the y and then the x, or you use this solve, the equation, then y of x and then the x. In the first case, the answer is given like a pure function. In the first case, the answer is given like a rule that assigns to y a pure function, if this function exists or is easy to find. Now, in the second case, the answer is given in this form: the y of x, the function evaluated at x, when it is a solution, is given by a certain formula. So in this case, this is a pure function. In this case, it's going to be the formula containing the x, just the formula of that function. It means if the function is, the solution is f of x equals x squared, in this case, the solution is just the f, the name of that function, or the function that converts x into x squared. But in this case, the function is given by the formula x squared. So it's given by the formula. Then, in the, let's see this example. Once we obtain the general solution of an equation, we can obtain particular solutions given values to the constant c1. Then, in this case, we are going to find the general solution of the differential equation y prime is equal to minus y over x. Then find a particular solution by making the constant c1 2. Find the value of that solution at x equals 5. Graph the solution when c1 takes the values -2, -1, 1, and 2. And then we are going to use in what follows the following variables. This variable with the name solution, list of solutions, numerical value, number value, non-value. We are clearing these values to assure that when there is a repeat use, when there is a repeated use of this part of the notebook, those variables don't keep values, don't keep those values assigned in previous repetition. Don't keep the values assigned in previous repetitions. And then here, we're going to clear this variable, this one, and this one. So let's press Shift Enter. And then, so now we are going to enter the equation. So you want to check whether the x and the y have values. You can enter the x and you can enter the y, different lines. You press Enter and you get x, y. So you don't have to clear them. You can either clear them or to check whether they have previous values. And then, so now this is the equation. Now we can use a symbol for the whole, to represent the whole equation. You don't want to write down the equation every time that you want to mention the equation. Here, you don't want to write it down again. You can use that name, equation. So you can start including that as part of the variables that you are going to clear at the beginning. Let me clear this. I can clear also the x and the y. I can clear all it is a good practice to clear all the variables that I'm going to use. And then I don't have to check that the x, y are, I have to clear all of them here, put the cursor. And then I don't have to check that the x and y don't have values. Okay, I already cleared them. I entered that equation. I can do this. I can enter a name for that equation. I can assign a name for that equation, which in this case is EQ. And then I can solve the equation using dissolve. Notice that we don't use the same command that we use to solve a regular equation. For differential equation, we use dissolve. And those rules that we are going to get here, defining the solutions, are going to be assigned to this. This symbol is going to be assigned to denote this list of rules. So you press Enter. And then you see that the solution is given by a rule like this, where the y is the function, the y represents the function, is the pure function which that assigns to any x the C1 divided by x. C1 divided by x. So it basically is, this is the function y equals C1 divided by x. Then if you want to, we can find the corresponding solution, the one corresponding to C1 equals 2. How can we do it? We take the y of x, and in y of x, we replace the y by that function, the one that converts this expression into C1 over x. And then we are going to replace the C1 that appears in the formula of the solution by 2. So you press Shift Enter, and you get that this is going to be the solution. Notice that if you don't want to get this parenthesis here, you can just take the part of the solution here. What part? I think this is going to be 1, 1, I think. Let me try again. Yes, you see that now you don't see the braces, because I took the part of this expression, exactly the rule that appears inside, you know. And then, so now what is the value of that solution at x equals 5? The numerical value is y of x again. We are going to replace this by the solution that we found, and then we are going to replace the C1 by 2, and then we're going to replace the x by 5. So we are applying all these rules to that expression, and then you get that in that case the numerical value is 2/5. Well, let me remember that you don't want to see the brackets. You can put here double bracket 1,1 to take the part of that of the solution which is exactly the rule, and then you press enter and you get the 2/5. Now if you want to get a numerical value for the 2/5, you enter this function here, and you get that the numerical value is in the decimal form is 0.5. Now if you want to graph the solutions that you found in to graph solutions asked in the question part C, we can obtain first a list formed by those solutions. Then the list of solutions is going to be y of x, where you replace the y of x by solutions. Remember, solute represents all the solutions. I'm going to consider these rules only what is inside without the braces, and then I'm going to replace the C1 by -2, -1, by 1, and by 2. Let's see what we get here. Yes, we get a list of all functions corresponding to these values of the C. And now, what do we have to do next? We have to graph the list of all solutions. We can graph all of them together. Notice that if it doesn't work, you can try to put evaluate here in front of list of solution, but in this case it works. In this case it works, and then this is going to be the solution. I don't know if the legend works in this case. Let's see. Let's see the case when we use the legends before for a plot. Yeah, we have to say plot legends and then an arrow and then expressions. Let's see if it works in this case. Not necessarily it's going to work, but let's try. So let me put here comma and then plot legends and then a dash, then the greater than, and now expressions between quotation expressions. And then quotation, and now let me graph it again. And then you see that it worked in this case. The blue one is -2/x. The orange one is -1/x. The green one is 1/x. And this one that looks almost like a red, or yeah, it's another, well, almost red, is 2/x. Is that right? So now, we have written all this code before, so that if you change just the differential equation at the beginning, you can do the same calculation as long as the calculations work for that equation. Let us see a different example here using the same code. It means that now the good thing about writing this down in this way is that you can use this code to do the same thing with other equations. For example, we can answer the same questions that we answered before for this equation here, for the equation y prime of x is equal to -y of x over x, for a new equation here that is going to be y prime plus 3/xy is equal to sine of x over x to the third. And then again here, I'm going to clear the solute, list of solutions, non-value, the equation, and I'm going to clear also the values of x and y. And then you press Shift Enter, and then we're going to use exact the same code. It means we are going to enter the equation. Of course, the equation is going to be different. This is the equation. Remember, you have to enter a differential equation like this. Put in the y. You don't enter y alone. You need to put the y as a function of x. Y depending on x. Okay, and then the equation, we are going to use the variable equation to name that equation, that differential equation. And then we are going to use this solve to find the solution of that equation. The equation is represented by EQ. And we're going to get the solution given as a pure function or a family of pure functions with respect to x. And we're going to use solute to represent that. Solute represents this. Notice that what is inside here, well, this is a list of a list, that the list inside the list has only one element, which is this rule of replacement. And then inside that, we have a function that has one element, which is in the rule in the right side has a pure function, which is that contains the number, the constant C1. And then we can find the solution corresponding to C1 equals 2. How can we do it? We can y of x, we can calculate y of x by using this rule of substitution. But remember, you don't want to see the brackets, I mean the braces. You can put here 1, 1, because in that way you're not going to see you're going to see only here. This represents only the part which is inside the two pair of braces, and then you evaluate at C1 when the C1 is replaced by 2. So you get what? You get this expression. And then you are going to find the value of this when the x is equal to 5. We're going to do it again, doing the same thing. So we're going to do the same thing that we did before. And then replace the y, in the y of x, to replace the y by that function, the pure function defined here, and the C1 by 2, but then the x by 5. In that way, we can get a value for that function. But of course, you get the exact value. You want to find an approximate value, you need to use the function n, and then you get an approximate value of that number. Now, you want to graph the solutions, you know, corresponding to values of x, values of C1 like -2, -1, 1, and 2. Well, we are going to define a list of solutions, y of x, where solute represents this family of solutions. But remember, we can here, to make it nicer, we are going to put here 1, 1 to get only the part of that solution, the one that we need. And then after that, we are going to replace the C1 by these values, by -2, 1, and 2. And then we get a list, we get the following. We get a list of functions. You know, notice that for different values of the C. Now you can plot this list of solutions using the same name that we use here. You put plus list of solutions. When the x go from -10 to 10, the plot legends is equal to expression. And then, well, here you get those solutions. You get these solutions here. And you have the legend here on the right side. Which one is which? And then solving initial value problems for differential equations. We can also solve initial value problems. Remember that first order initial value problems are like this. The y prime of x is equal to f of x comma y, where the y of x sub 0 is y sub 0. And then to do that, we are going to use this format. the same Wolfram language function, this solve, but then in between braces, we are going to put first the differential equation, then the condition. But notice that we use double equal sign for both, And then, but there is something missing here. So I need to close the brace here. And then if you want functions, pure function, you put the y and then the x. To tell the program that you want to, these are differential equation with respect to the x. And then in this case, we are entering this differential equation. And then we are going to solve the differential equation together with this initial condition. So I'm not using a name for the differential equation, but I can do it. But I didn't do it here. I repeat that expression here. Just I copy and paste it, something that we can do. And then it's not very convenient when you want to use the same code and to enter a different equation, because you need to do the copy and paste also for the new equation. So it means that here probably it's better to call this EQ, like as we did before. Let me clear the EQ. So I have to clear EQ and clear, well, I'm introducing a new name here, Solute2. This is a new name. I'm going to clear the x and the y just in case also. Well, it should be enough. Well, I have to copy this because I entered this as a text. So I need to copy this part here, and then you put the cursor here. When you see that the cursor looks like a horizontal line, here, you click, and then you are going to enter. By default, you can enter anything like an input here. You press Ctrl V to paste it. And now you are going to press Shift Enter to enter that expression. Now you're going to call this, remember, we are entering the equation and we are calling the equation EQ. Now we are going to solve EQ, the equation here. Let me erase this. And then we have EQ, the solve EQ, and then with this initial condition that appears here with respect to y and then with respect to x. So then you press Shift Enter, and you're going to assign the solution, the rules that you obtain is going to be assigned to this name. Or the name is going to be assigned to those solutions. So then you press Enter, and then this is what you get. But what they say here, they say that this function, the formula is a little bit difficult to express because it cannot be expressed so simple. And they tell you that your function is the inverse function of the function e to the y or e to the x plus sine of x. So the inverse function of this function is the one that when you evaluate it at this expression gives the solution. Okay, it doesn't do the simplification here because it's impossible. It's difficult to do it. But this is our function. And then if you want to graph that function, what can you do here? You can, remember, you can go and take solute, and then these are rules of assignments. You are assigning to y this function that is defined by this expression. And then we are going to graph that function, replacing the function y of x, replacing the y by using this rule here. And when the x is between -5 and 5. Let's see if this works. Yes, it shows the solution of that equation, even though it cannot find the exact formula for the function. It knows that this function is the inverse of the function e to the x plus sine of x, which is difficult to find explicitly, evaluated at 1 minus x plus x squared over 2. And this is the graph of the function. Now, together with this, we can graph the point corresponding to 0, 0. How can we graph the point corresponding to 0, 0? You put the point, you use the function point, and then you put here the point in between braces. You put inside the brackets, you put the point 0, 0 in between braces. Then you put red because you want the point to look red, to have this color, and then the point size large to make the point large. If you don't introduce this, then the point is going to be very small. And if you introduce this option red, then the point is going to be black. And then, well, here by default, and then we have like braces that go from here to here. This brace opens here and ends here. And then we can graph the point alone. But that point alone is at the right position. But as I don't see the axis here or anything, it doesn't tell me anything. Now, I can graph both graphs together. If you want to graph F1, the graph 1 and the graph 2 together, you can use a command that is called show. Show graph 1 and graph 2 together. Then you press Shift Enter and you get this graph here. Okay, and then this is the solution passing through 0, 0. This is the solution passing through 0, 0. Then notice that show is very convenient when you have more than one graph and you want to put the graph together. Of course, we might have written the show from the beginning, show and then plot this. You open a brace and you put the plot for the graph 1. Instead of naming that graph by graph 1, you enter the graph and you enter the other graph, graphics, point, etc. And you put everything and you get the same result. Now, we can also solve this equation using Wolfram alpha input. Notice that in this case, the solution is not solved for y. It is given as an implicit solution. Then, well, imagine that you want to solve this initial value problem. You have to solve. You enter, remember, to enter to set up a Wolfram alpha input, when you enter the input, you need to click here and you go to Wolfram alpha query. This is when you get this symbol here. And then you enter this in words. Solve the initial value problem, y1 is equal to minus 1 plus x divided by e raised to y plus cosine of y. Notice that we don't have to put it like y over x, and you can put just the y. And where the y of 0 is 0. And we don't have to put double equal signs in that case because you are using a regular language. You are using regular language. And then in some, what happens in this case? Let me see what we get. You press Shift Enter. And then let me close this window here. And basically, this is what we get here. The output is like the output given by Wolfram alpha. You see, the equation, it is rewritten this way: y prime of x is minus 1 plus x divided by e raised to y of x plus cosine of y of x. That is separable. It can be expressed in this way. And then it finds this implicit equation. In this case, it doesn't try to solve for y. And then actually, if you want to see the step-by-step solution, you can click here, and it is going to return the step-by-step solution of that equation, something that is not for free when you are using Wolfram Alpha. But okay, let me continue because I don't want to take the whole time. It takes a while here because, well, these are the steps. These are the steps. It moves solve the separable equation. It moves this part containing the y to the right side, and then it integrates both sides with respect to x. And then in the left side, it produces this. In the right side, it produces this. And that's it. This is the way of solving that equation. But the Wolfram language, it says that if this function has an inverse function, then the f of y is equal to this. Then the f of y is e to the y plus sine of y. Then it moves that f to the other side as the inverse function. It doesn't represent it in a concrete way, but it says inverse function in front of this. And then, so now, this is the last example. The last example. So this is an implicit okay, well, let's do this before. Well, we have two more examples here. It says, in some cases, the solution of differential equation cannot be expressed by a family of explicit solution. In cases like that, the solution is given by an implicit equation in the form, solve this for y of x. When the program, when Wolfram language doesn't know how to solve the implicit solution that, or the family of implicit solution that it gets, what it does is to express the answer in this form, solve an implicit equation and then for y of x. This is the way of giving the solution when the solution is in general is given by an implicit equation. So let me show you this example. Solve the initial value problem y prime is equal to minus y cosine of y divided by x cosine of y minus sine of y, where with the initial condition y of 1 is equal to 2. And then graph the solution together with the point 1, 2. So we're going to use the variable solute as we did it before. So we're going to clear all value for this variable. And then we're going to solve the initial value problem. Well, first we can solve yeah, this is the initial value problem. Notice that the equation goes from here to here. This is the differential equation, and then this is the initial condition. We need to put both in between braces and separated by commas. We need to use double equal sign for both. And then we have the y of x here and x. And then here, you press Shift Enter. And this is going to be the equation. This equation is a little difficult to be solved for the y. That's why it doesn't express the solution as an assignment rule, as a replacement rule. It says that if you solve this equation for y, then you get the solution. But the program doesn't know how to solve it. That's why it leaves this indicated. And then in that solution, in what is inside here, which is number 1, it replaces the y of, we can replace the y of x by y to make it like an implicit equation that depends on x and y only, without putting y of x. So this is going to be the equation when we replace the y of x by y, only the equation. Now we can graph it as it is now. We can graph it. So, but if you put here this without putting evaluate, this is not going to work. Okay, it's not going to work. That's why we have to put evaluate here. Evaluate solution, the part one of the solution, when you replace the y of x by y in between, in this interval. So you press shift enter, and even though we cannot solve the equation for y, it produces a graph for that solution. Now, if you want we want, for example, to plot also the point corresponding to the initial condition, which is 1, 2, to see that it belongs to that. And then how can we do it? We can use show, and then we include this graph again that we have before, control plot, evaluate. This is the graph that we have before. I mean, this is the command producing that graph. This is the command from here to here. Now, the other one is going to be the command showing the point 1, 2. And why the expression is so long? Because we have to include here what? That this is the point 1, 2. We need to use braces for the 1, 2. We need to specify that we want this to be represented in red, and we want to represent also that the point size is large in this case. And then it means that we are graphing the two. The show tells you that we are going to put these two graphs together. And then you put the cursor over there, you press Control V to, sorry, no Control V. I pasted something here. Yeah, I know what I pasted, so I can eliminate that. So now point, and now you press shift enter, sorry, and you get both graphs together. The graph of the implicit equation and the graph of the point together. So this is the point 1, 2, and you see that this part of the graph passes through that point. Now, this is the last example. The last example, I can change the format of this to make it, for example, I highlight example, I can, this is what? This is text. I don't want to change this format, but I can change this to a boldface to make it nicer here. Now, given the implicit equation sine of x sine of y is equal to 4 times x times y plus 1 minus pi to the second, that has the point pi over 2 comma pi over 2 as a solution, do the following. Then construct an initial value problem that has the previous implicit solution as the solution, as one solution, as a solution. Well, initial value problem as the solution, yes, because it's the initial value problem. And then graph the initial solution and the corresponding point given by the initial conditions. By the initial condition, in this case, it's only one. And then graph several solutions of the given differential equation. So we can start differentiating both sides of the given equation with respect to x, treating the y as a function of x. So we're going to start clearing these variables that we're going to use in what follows here. We're going to use a name EQ for that equation. So the name EQ for that equation, so you press enter, and now we are representing that equation by EQ. Now we can differentiate that equation with respect to x using this way of differentiating. So, and we're going to represent this by SO, by SO. And then you get, this is the equation. Now we're going to solve that equation with respect to y prime. Notice that when we solve, we have the y prime over here, we have the y prime over here, and we want to solve that equation for y prime to get the equation, the differential equation written in the normal form. So you press enter, And now you see that it is solved for y prime of x, but it doesn't say here y prime of x is equal to that. It is given like a replacement rule. You know that whenever you have y prime, it's replaced by that. And then what can we do here? I want to get the equation, but to get this part of that expression of this list, I can use this S01. You take the part 1, 1, 2, and this is going to give you exactly this part here. And then let's check it. Let's check it. So it does give this part of the list. Now we are going to define the following equation. Equation EQ1 is going to be y1 prime equal to that expression that we have before. So shift enter, and then this is our equation. Now we are going to solve this equation, the initial value problem formed by this equation, and the initial condition y of pi over 2 is equal to pi over 2. And we're going to get a rule that is going to give you the expression of the solutions. So now we press enter, shift enter, and notice that the equation, the solution that is given here is exactly the same equation that we have at the beginning. So we have an equation at the beginning, and given that equation, by differentiating both sides, we obtain a differential equation, and solving for y prime, we obtain a differential equation. Now, solving that equation, we obtain back the same implicit equation. But notice that it doesn't know how to solve for y of x in this case, because we have the y of x here, we have the y of x here. And as it doesn't know how to solve for y of x, it says that the solution is given by this implicit equation, but it says, well, solve for, of course, you solve it for y of x, but it doesn't know how to solve it. That's why it expresses the answer in this way. Solve this equation with respect to y of x. It means it's answering the question like with another question. Can you solve this equation for y of x? If you can, this is going to be the solution. But then we cannot do it, because if the Wolfram language doesn't do it, it's because this is going to be a very hard problem. And then we are going to do the following. We are going to define S03 as the S of 2, double bracket, 1, double bracket, to get only the equation, to get only this equation. And in that equation, we're going to replace the y of x by y, because otherwise we cannot use the graph. We cannot graph it using counter plot. And then we are going to obtain what? We are going to obtain just the equation, but where we have replaced the y of x by y. And now we are going to graph using counter plot. We are going to use this, to graph this implicit equation. And we are going also to graph together with the whole part here, this second part here, is to graph the point, to graph the corresponding point. And then, so we're going to graph them together using show. And then notice that we use here evaluate, because if you put the SO3 here only, this might not work. Okay, and then in that case, it's a good idea to put evaluate. And then you press shift plus enter, and you get, you see, this is the solution is formed by this curve over here, this curve over here, and this is going to be the point. And now we can also solve this differential equation without considering any initial condition. Again, let me clear S of 2 and S of 3, and now I'm going to denote by, I'm going to use S of SO2 to the solution, to denote the solution of that equation that we had at the beginning with respect to x. as a differential equation, of course. What do you get? You get that, but now the C1 is an arbitrary constant. When we solved the initial value problem, the C1 was a certain value. But again, notice that it says solve this with respect to y of x, because it doesn't know how to solve it. It's an implicit equation. And then we can get the left side of the equation in the previous equation. We can replace the y of x. Well, this expression is the one that we have denoted by SO2, and then in S of 2 we take the part 1, 1, which is exactly the equation. If you put let's say 1, 2, is going to be this part here probably. Well, here you need to check it. And then S of 3 is this part, the equation, that is the equation where y of x is replaced by y. And now we can use, we notice that, well, we are taking here only that's why we have the second one here, because we are not considering the whole equation. The whole equation is only S of 2 at 1, double bracket, 1, double bracket. But as we have here two parts, the first part is 1, the second part is 1. So that's why this is 1, 1 here. To get only the first part without taking the constant, And then if you want to find a family of solutions for which the left side of the equation is this and the right side is whatever constant, you can do it like this. Contour plot. Notice that now we don't enter an equation, we enter only this equation that depends on x and y, and we enter the window, and then it is going to return. When you press enter here, you get a family, some solutions represented for different values of c. It doesn't tell you what values of c is using. It finds those values of c automatically. But notice that in this case, we put only the left side of the equation, and the program itself determines what values of c to pick. And then notice that it produces a very nice graph. And then conclusion. As we mentioned in the notebook, the intention is not to, the intention of this notebook is to propitiate a first encounter of the differential equation student with the great possibilities offered by Wolfram Language to solve problems in the area, and then to continue learning about the applications of Wolfram Language to solve ordinary differential equations and other mathematics problems. You can use these links. You know, these links, these are parts here that you can also find directly using the documentation. If you go to documentation, you find many of these things here. And then you can learn a lot about how to use Wolfram Language. You see, you can go to fast introduction book and course, archives and repositories, developer resources, Wolfram Language products, and so forth. So working in notebooks, so you can creating and organizing interfaces, working with data. There is a lot to learn with Mathematica. It's a nice program, but you don't have to be a specialist in Wolfram Language to be able to do the project that I'm going to assign soon. And then the purpose of this is you to start getting familiar with that and to start seeing how to use the different tools offered by this website. Okay, thank you very much and have a nice day. So I'm going to stop sharing my screen and I'm going to stop the recording. Have a good day.